We are going to try to see if we can predict whether a precipitate will happen or not. And what was a precipitate again? What was a precipitate? Yeah, solid forms, right? It's kind of important. It could gunk up the pipes. It could gunk up a lot of stuff, right? Or you want to know if maybe you want that gunk to come out, right? Or maybe you don't want it to come out. It would be really nice to be able to predict whether that's going to happen or not and what it's going to be. So there's a lot of usefulness to what we're talking about. And I know even the EPA does this a lot because it's not only in the test they would precipitate out this bad stuff and see if it's there, and plus they would get it out of the environment. So here's a KSP table. I changed a few things just like usual in the morning, but well, not too much. Okay, so what we're going to talk about first before we get started, I look at this as something that will help you because it'll make the problems less frustrating if you're aware of this happening. Because it's a lot easier to if you can recognize what definitely is not going to form a precipitate, your life is going to be a lot easier. So for those of you who do not have a photographic memory, I copied and pasted a solubility rule table in here. But what cations, we talked about this several times, what cations can never, ever, 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 ever form precipitate? The alkali metals, which is group number 1. The group 1. And if you want to read the table, that's what it says too. The group 1. There's also, now you probably need to look at the solubility rules for this one. Megan, there's one more cation. We'll never make a solid with anything in water, never make a precipitate. It's in the table. Lithium's in group 1, sodium in group 1. Do you see it? That's group 1. NH4. What do they call this? Ammonium, right? So ammonium. And group 1s. Never get a precipitate. Does that mean you can't get a solid out of this stuff, Kendall? I can never have ammonium carbonate. I can never find a bottle that says ammonium carbonate and have it be a solid. So what I mean is can that exist? Can ammonia make solids? Just suck all the what out? All the water. And then all you're going to be left with is the crud on the bottom, and it'll be ammonium, whatever, right? So but that's not a precipitate, right? That's sucking out all the water and drying everything out. So we're not talking about that. Okay, now there's some anions. So just try to remember that the group 1 metals, ammonium, never form precipitates in water. Anions, this will help you too. Cameron, now you pretty much have to look at the solubility rules because I don't think we ever talked about this. There's some anions that you can never make a precipitate with. What would they be? Can you see them in there? Anybody help them out? Anions have what charge? Negative. So you got to be looking for something negative in here, right? And then you got to use their jargon. All this stuff soluble. Just like they said up here, all soluble. So that means never ever form precipitate. So there's your answers. Nitrate, acetate, chlorate, and perchlorate. So this is not, again, I don't feel this is something you need to memorize. It's not going to kill you or break you. It's just going to make your life less frustrating if you are aware of it. Okay? Because we're going to end up doing stuff like this.
In precipitation reactions, an insoluble product or precipitate is formed. Precipitation reactions usually involve ionic compounds. Let's study precipitation reactions by considering the 3 aqueous solutions shown. Click on the 2 solutions you would like to mix, then answer the 2 questions. The animation will play after you answer the questions.
Okay, so I'm just going to pick 2, and then you guys are going to predict. I'm going to pick this solution. I'm going to take this one, dump it into this one. So the question is, will a precipitate form? And if so, what would it be? So so you can see the rules there. You remember, all you're doing, Jose, is you're just picking that one cation with one solution, dumping it with the anion of the other solution, right? And combining them and predicting whether they make a precipitate or not. And I guess what I'm saying, Jose, is like the sodium would go with the, what's the NO3 called?
I can see it.
Oh, step up closer, man. You can't see this?
No.
How about now?
Yeah.
Okay, the sodium goes with the NO3. The Cl minus goes with the Ag. There's only one possibility here for a precipitate. If you remember the little hints I gave you, it would be what? Right? It has to be, which one? AgCl. Remember, NaNO3 is a waste of time. Ain't going to work. You see how life is going to be much less frustrating if you remember that rule. You're not going to get the wrong answers. Just life will be so much easier. So you don't even mess with looking at NaNO3. Your only possibility is AgCl. And pretty much all you do is you look and see, whoop, where'd it go? See if it has a KSP. And then you have a problem to do. So you're going to waste your time looking for sodium nitrate in this table is what I'm trying to get you to see. So half the work if you have an idea what the solubility rules are. Okay, so now, did we see it? Yeah. AgCl's in there. Great. Has a KSP.
When solutions of 0.1 molar sodium chloride, NaCl, and 0.1 molar silver nitrate, AgNO3, are mixed, silver chloride, AgCl solid, precipitates. Checking the solubility rules, most chloride ionic compounds are soluble. However, silver plus 1 combines with chloride to form silver chloride, which is insoluble in water.
All right, so it starts forming a crystalline structure back there.
In precipitation reactions,
Whoa.
an insoluble product or precipitate is formed. Precipitation reactions.
Can I interrupt him? Let's try that. Yeah, let me interrupt him. Great. Okay, these two. Mia, what precipitate would you predict? The Ag with the OH, exactly, right? Because the nitrate you know is a no-no. The K you know is a no-no. So AgOH. Look and see if it has a KSP. It does. So dang right. And she said AgOH.
When solutions of 0.1 molar silver nitrate, AgNO3, and 0.1 molar potassium hydroxide, KOH, are mixed, silver hydroxide, AgOH solid, precipitates. Checking the solubility rules, most hydroxide salts are insoluble. The only soluble hydroxides are alkali metal cations and barium 2+ ions combined with hydroxide. In precipitation reactions,
okay, I think what's left? This one and this one, right? Okay. Who do I have here? Stephanie. Will a precipitate form, and if so, what? What would be your best guess as to its identity? Is there? What's that? Well, you can't do an anion and an anion though. K won't work. Either will Na. So yeah, there's no way. You can't get a precipitate out of this. So we answer no. So you'd be wasting your time looking in the KSP table, trying to do all the math.
Why won't K work?
Because it's in group 1. So it won't work with anything. What happened to the guy's voice? He got all pissed because I interrupted him. All right. Okay, so stuff just keeps floating around. So we're going to try to answer this question and get a game plan here. We have a solid goes to its ions, right? And it's going to be a little complicated because they're going to, let me show you what the problem's going to look like. Here, 45 mils of this concentration of this compound was added to this many mils of this concentration of this compound. So when you're looking at this, what we did so far is okay. We know how to handle the first part. What would be the possible precipitate? Anybody? Off your top of your head, what would be the possible precipitate? Ba with F. I totally agree, right? Ba with the F. So what you do is you can verify it. Barium fluoride. Kind of nice because look, you said Ba with the F, and the right chemical formula will be here if you forgot about the 2. So BaF2 is going to be it. But you got to calculate concentrations. So we need a game plan of this. So with BAF, I would expect to precipitate, but okay. But if it's not concentrated enough, it's not going to form a precipitate. So that's where this life gets more complicated. This is real life stuff. So it's not always going to form a precipitate, not if it's not concentrated enough. So what we need to do is determine the concentrations, substitute into our, oh, we didn't write it. We can't substitute if we didn't write it. So instead of writing a KSP expression, KSP is always products over reactants, right? Well, we're not going to call it KSP. We're going to call it QC because we don't know if it's going to form a precipitate or not. We don't know if it's at equilibrium or not. So, but it's the same products over reactants. So it would be concentration of B raised to the V. Concentration of C raised to the little c. All over 1. So the problem is getting those concentrations. You have to calculate them. But no worries, Andromeda remembers. What's concentration? What unit do we use for concentration all the time? The big M. And the big M is always what over what? Moles over liters. Figure out the moles, figure out the liters, and just remember the trick. You dumped one solution into one solution, so you have to add those volumes, right? So, and we go ahead and we get a number for this, right? Substitute in our QC expression, really our KSP expression, get a number and compare it to the KSP in the table, right? Because this is in the table. And if it's exactly equal, I think the book says that yes, you see, because technically you're not going to see a whole lot, but somewhere in there is a little tiny crystal floating around. So they're saying technically, yes, you have a precipitate if it's equal. If QC is less than KSP, you go through all this work, and QC is too small, would you have a solid floating around? Steph, what do you say? No. Because remember, all equilibrium constants are products over reactants. If the number's too small, you don't have enough product, right? So it needs more. It's going to dissolve even more. If QC is less than KSP, it's really informative. It means more of the solid is going to dissolve. You better be ready for that, if that was an application. So no precipitate. So definitely, if QC is bigger than KSP, you've got too much product. That means you have too many ions. So it has to shift and make more solid. So there's your precipitate. Yes. Okay. So let's try some of these. That's our game plan. Identify what the possible precipitate is, calculate concentrations, substitute into our pretend KSP expression, we call it QC, and just compare QC to KSP in the table. And we'll have one of 3 results, always. So here we go. We're starting out kind of easy here, Kenneth, though, because I'm not having you calculate any concentrations. I'm giving them to you, right? In fact, we're not even mixing 2 solutions. How would you handle this? I think it always starts, though, with identifying what the solid's going to be. What's your only choice here? PbCl2. I totally agree. So I think it's easiest if you write the KSP reaction. If you write the KSP reaction, then it's a lot easier to write the KSP expression. So Bowdy, he's right. PbCl2, I think, is going to be the solid. And we can verify it. We're going to have to look it up anyway. Where is it? Here it is. 1.2 times 10 to the negative 5. So that's going to be our KSP. Okay, but we're supposed to write this QC expression. So Bowdy, what do we do? Oh, we never wrote the reaction. Let's do that first. Bowdy, let me ask you that. How do you write the KSP reaction? What goes to what? Remember, it's always the solid going to its ions. PbCl2 goes to Pb plus 2 and 2Cl minus. It's perfect. Right. I think it's always a good idea to write this. I was so ready to jump in and write the QC expression, but I think you should write this first, because then you won't screw up. Well, odds of screwing up are less. Megan? Yeah? Kenna? Did I look up the wrong number? 1.6 times 10 to the negative 5. Thank you, Kenna. Okay. Who am I picking? Megan, how do you write the QC expression then? Yeah. Oh yeah, you can put those in. Yeah, let's just do this first though. So otherwise we might lose somebody. Times. And where do you put the 2? Superscript. Yeah, you got to square it all over 1. Okay, now I'd put the numbers in. You got the 0.035. You got the chloride squared. So what do you get for a QC? Once we go through the whole thing, Bowdy, it might help you. We'll finish it. I got 7.9 times 10 to the negative 4 about. Did you guys get that? Yeah. So around 7.9 or so times 10 to the negative 4. So what we did is we... Really? 0.035 times 0.15, and you got to square it.
No, you just have to square it first and then multiply.
7.8 times 10 to the negative 5. So 7.8 times 10 to the negative 4. My goodness. That's right. That's right. All right. Okay, so we're good? Okay, so this is our QC. So the whole question is will it precipitate form? So we're always supposed to say yes or no. That's our answer. So if QC is 10 to the negative 4, KSP is 10 to the negative 5, QC is too big. And the negative signs always kind of screw you up, right? Just realize this is, right, a decimal point, four zeros there. Here's a decimal point with only 3 zeros. So this is 10 times bigger. QC is too big, so yes, we will see it precipitate. Okay. So the game plan, now the questions are definitely going to get more complicated here, but the game plan remains the same. You identify what the precipitate's going to be, make sure it's in the KSP table so you didn't screw up, write the KSP reaction, write the QC expression, calculate concentrations if you have to, and you're going to have to in the next one, and then compare your QC to the KSP. So give it a shot. Here's your first one, and then we'll go through it. So identify what you think the solid's going to be. The best bet. Save time by not looking at alkali metals and nitrate, acetate, chlorate. My calculator works in the dark.
Mine half works.
Yours doesn't?
Like half of the time.
Yeah, half is half. I like the dark.
You like the dark.
Okay, so identify what it is, and then I would write the KSP expression, the QC expression. So you have these concentrations, right? And then for each concentration, you have to figure out the moles and the liters. So to get the liters, you're going to have to add up those 2 milliliters and convert them into liters, right? Because it got diluted, right? Because that's a really good question. That barium should be 0.0015 molar. Why not plug it in? It would if all you had was 45 mils of solution of it. But you dumped in 75 mils of something else. You screwed up everybody's concentration. You screwed up the potassium fluoride's concentration of 0.0025 by dumping in the 45 mils of something else. See, add the liters. Add to get total liters. But I don't like doing this right away. I like just following the logic first. I don't do stuff until I have to. So I would start out by writing the KSP reaction. And you're saying it's barium fluoride, because we talked about it already. Right? And then it has a KSP, which is, what is it? 1 times 10 to the negative 6. Okay, so you write your QC expression. Hopefully you wrote barium and fluoride squared. So now you got to calculate each concentration. Calculate that concentration of barium. Calculate that concentration of fluoride. And remember, Andromeda told us the concentration is always what? Moles over liters. Figure out what each one is. Right? Take that number and substitute them in up here. Remember, how do you get moles?
I'll remember it again right now.
Yeah, how do you... Oh, no, that's not molar mass.
Oh, okay.
It's, you have to set up the big M equation. Because like here, you know the big M... Exactly.
Okay.
It's going to be that times that.
Okay.
Because the liters would... Yep, exactly. So how did you guys get the moles of the barium? What did you multiply by? Good. 0.045 liters times 0.0015 moles per liter. Right, you can either set up the big M equation or just remember, oh yeah, multiply liters times big M, I get moles. So that's how you get the moles. Do the same for the fluoride. The liters, you got to add up, what, 0.045 and 0.075. about 5.63 times 10 negative 4 is what I got. So I got about 5.63 times 10 negative 4. For fluoride, so you got to take it's the concentration, the big M, the volume of it times big M. So that would, for the fluoride one, it would be these two. 0.075. Here's your volume. There's your concentration. That's what you use to get the fluoride one. See if you can get that for your QC, 1.37 times 10 negative 9. Where did I lose you, Bowdy?
Oh, I have a question, but it doesn't really have to do with this.
That's fine. What's the question?
Well, it's because you know how, like, when you do, like, ice equations, if there's, like, a coefficient, like, you know how around how, like, a 2F?
Uh-huh.
But then you're doing, like, I don't know, kind of like the QC thing, but with a different thing.
So
does it become an exponent? Or does it become
yeah, just
2X?
I think things get confusing because Q is just, you don't even have to write Q. It looks confusing. Just write KSP prime or something, because all you're trying to do is calculate KSP and see if KSP is too big or too small. So that means since it's writing a K, that means you're writing equilibrium constant expressions. Coefficients always become exponents. There is no ice table, ever.
Yeah, I know, but I'm just confused about ice tables now.
Yeah, so with ice tables, these come in front of the x.
So it would be like plus 2X.
Yes, if you're making an ice
But
table.
then when you were writing, like,
And then when you write equilibrium constant expressions, those coefficients become exponents.
okay.
There's two different things.
Yeah, I know we don't need it now. That's why
There's just two different things. So just remember, those coefficients, they do a lot. Those coefficients are the charge on the other compound. They use them to balance things. But in ice tables, those coefficients become 2x and stuff, right? In equilibrium constant expressions, they become powers. So did you get 1.37 times 10 negative 9? So will you have a precipitate? No, too small. Okay. So if you can do this one, I'd say you are set and ready for the homework. The big test.
The only thing I can think about is it's just a simple math algebra. So because I add these two and I multiply these two and squared, yeah.
Yeah. Oh, sorry. What are you
No,
doing?
no, right.
Oh,
just for the
yeah. Okay, you
M?
didn't write the QC expression. Yeah, so this is the moles over the total volume. Because I think you have to realize, yeah, it'd be nice just to plug that in for big M.
Mm-hmm.
And it would be if it was just this, but they screwed it up.
So there will be problems where like there's nothing like this. There isn't one.
Well, yeah, it'd have to look like this.
Where they don't say it at all. Okay.
Yeah. If they give you volumes, you're gonna have to add them. Did anyone figure out what the solid's going to be for 52? PbCl2. Good. Those coefficients will kill you if you don't use them.
Hey, Dr. Smith, I'm confused because you kind of did that one in the problem over here, but the KSP is different from the one on the table.
Really?
Yeah, it says.
Well, you have to use the KSP whatever's in the table, because I think, yeah, your table is different than mine. That's weird. They should all have the same KSP. So whichever one you use. What does your table say?
It says 1.6 times 10 to the negative 5.
Well, let's just use that one then.
In
That
this
works.
problem, we used the 1.2.
Just use whatever's in your table. They might be at different temperatures or something. So you have no choice. You have to use the KSP in the table that's given to you. So. So QC is 2 on this last one. 10 to negative, I got 10 to negative 6. Did you get 10 to negative 6? Okay, so 10 to negative 6 and comparing 10 to negative 5. So it's too small, so QC is too small. That means what precipitate? None, no precipitate. Clear solutions, solution stays clear. No cloudiness, no precipitate. Okay, so